Good evening, good evening. Good morning. See, I was in Portugal 2 days ago, so my brain is still in Portugal, I guess. Thank you for the invitation. Such a pleasure to be here. This is my conflict of interest slide. I do work for several companies, mostly for medication development. My main conflict of interest, though, is probably that I'm also celebrating my silver anniversary of smoking. Unfortunately, I've been a smoker for that many years. I've tried most of the medication in the lab first, and then on myself. Some are not that great, others are very good, but that hasn't worked yet on me. And ground submission didn't help. Right. The number one cause of relapse for me. So I'm going to take you on a little journey from the behavior all the way to the neuron, the synapse, and the drug, and to try to develop a framework of the dark side of nicotine. So what is the dark side? Well, everybody knows the light side, the bright side of nicotine, the positive reinforcement that develops thanks to the mild euphoria created by nicotine, the anti-nociception effect, the mood regulation. It's beautiful. It brings you up when you're down, brings you down when you're up. The cognitive enhancement for grant writing. So those effects are really important, right? But they don't last very long. Right? They last minutes, hours, and that's pretty much it. And you can become tolerant to some of those effects. What is most interesting to me is obviously the dark side, this irritability, this anxiety, the cognitive deficit, the insomnia, and the craving. Okay? My wife always tells me when I quit, go back to smoking. Very supportive wife. I love her to death. And those effects last much longer, days, weeks, months, years. They're very difficult to get rid of them. So there was an issue in the literature, particularly in the preclinical world, because one of the cardinal symptoms of the dark side in animal model is the fact that when you give animal access, extended access to the drug using self-administration, you give them 6 hours, 12 hours, 23 hours a day to cocaine, heroin, methamphetamine, you see that they will progressively escalate their intake. And the idea is that this is because they develop symptoms of dependence, they're craving the drug more and more, and every day they are going through an acute withdrawal that they're trying to compensate the next day. Whoops. The problem is with nicotine, you do not observe that. Okay, this is the seminal work by Athena Marcu that I had the chance to work with at Scripps for a little bit. And she wouldn't see any escalation of nicotine intake when you give animal access, long access to nicotine. And a lot of people have argued that, well, it's obvious, it's because nicotine is not that addictive, right? And so maybe nicotine is a different beast in terms of drug compared to all the other drugs of abuse. We replicated this work where you see that you have a flat line when you give them extended access to nicotine self-administration. Now the trick is if you give them a combination of extended access and intermittent access, then you do see this escalation of nicotine intake. And so we've shown that the critical factor here is really the combination of the long access and the intermittent access. And it takes at least a couple of days to show this escalation of intake. So the animal, after 2 days, 3 days, they will take 50%, 70%, 100% more nicotine. So this nicotine deprivation effect is important for driving the nicotine self-administration. So the idea behind here is that during this early withdrawal, you have the activation of a brain stress system. And like Imad mentioning to you, what we've been looking at is the corticotropin releasing factor system in the brain, not really the projection to the, not really the neuron in the hypothalamus projecting to the pituitary, but the neurons that are located in the amygdala, okay, the extra hypothalamic CRF system. We've shown that you have a release of CRF in the amygdala during withdrawal. If you give CRF1 specific antagonist, you can reduce this nicotine deprivation effect or this escalation of nicotine intake. At the same time, you can also reverse the effect of acute withdrawal on hyperalgesia and on anxiety-like behavior by giving this CRF1 antagonist. So at the behavioral level, the dark side, what it is, it's the somatic signs, the physical pain, the emotional pain. It is a very powerful driving force for the consumption of nicotine. A lot of people criticize the fact that this research doesn't address the long-term abstinence and that most of the symptoms disappear. But in terms of harm reduction, I think it is a critical phase and that we can do we can get a lot of benefits in terms of health if we can address this dark side, because we could reduce exposure to tobacco. And then the activation of the CRF system, obviously, is critical. So can we identify the neuronal network of the dark side? So for many years, what people have done is looking at region of interest, like the accumbens, the VTA, the prefrontal cortex. The problem with this approach, and we've done it, it's great. We find brain regions that are key for those symptoms, but it's very narrow, and we miss 90% of the brain. So the approach that we've developed is a single-cell whole brain imaging of the brain. So we use mice to do that. We expose them to nicotine, we make them dependent, and then we harvest the brain during early withdrawal. And we use the iDisco approach combined with light sheet imaging. We automatically detect every single neuron in the brain, quantify them, register them on the Allen Atlas, and then do some fun statistical analysis to try to understand what's going on at the network level. So what does it look like? This is not nicotine, this is cocaine. If it loads at some point, what you're about to see, maybe it's a brain after administration of cocaine. There you go. Each dot in that brain, every flickering dot is a neuron that has been activated by cocaine. So you see that you can go through the entire brain. This is top to bottom view. So it's very useful, and you can quantify the entire brain in a matter of hours. What it would take you several years from a graduate student to do the same work. So what does your brain, or your rat's brain on nicotine look like? So this is what it looks like. You have about 200 brain regions. This is the saline group, the nicotine withdrawal group. You can see that the red means the brain regions are positively correlated, not only with each other, but they have the same pattern of correlation with the rest of the brain region. You have about 9 or 10 big modules in the saline group. When you look in details into these modules, you have a region that work together, that are correlated together. Okay? Visual cortex, visual thalamus cluster together, sensory motor cortical area cluster together, a normal brain. Right? During nicotine withdrawal, you see that all that is shattered. Right? And you have a massive decrease in modularity. The number of modules decrease. No matter how you cut that tree here, you will always end up with less modules in the nicotine group. How does it compare to other drugs, you may ask? It is very similar to withdrawal from other drugs of abuse. It takes some time to load because those figures are gigantic. We had to buy a printer that is about 5 feet long to be able to see what brain region we're looking at. So if you compare to alcohol withdrawal, methamphetamine withdrawal, and cocaine withdrawal, you see the same pattern again. You have a decreased modularity in all those withdrawal. Cocaine and methamphetamine very similar. Nicotine is slightly different, but you see you have the same decrease in modularity. So what are those brain regions? Well, if you look at that first big module, you have every single amygdala region. Central amygdala, basolateral, lateral, intercalated cells, cortical amygdala, piriform amygdala area. And you have 2 brain regions that have been critically involved in nicotine dependence and nicotine reward, which is the ventral tegmental area and the interpeduncular nucleus. So this is great. I mean, what people have been doing in the past is right spot on, right? Those brain regions are critical. We're still missing 90% of them, right? So there's a lot of work that can be done to further precise the relationship between all those brain regions. So we wanted to do a little more sophisticated analysis and try to understand the network. To do that, we use graph theory. Most people do not know what graph theory are, but they are using it every day. If you came here using Google Maps, you use graph theory to try to find the shortest path. If you are using those social network, you are using graph theory. I'm sure you've been on social network and all of a sudden you have an ad coming up to buy a microwave, for example, and you're like, how do they know I need one? They use graph theory, right? This is what I was presenting, working on that talk. That's my suggestion for me. Scientists taught SEALs to sing the Star Wars theme with hilarious results. I love animals. I'm a big fan of Star Wars. I mean, it's spot on, right? So it has to be a good approach, right? So we use that to try to discover the neuronal network. And again, we see these two massive modules that are creating that network. The more red a network, brain region is, the more important that brain region is for the function of each module. And the bigger the circle is, the more important that brain region is to communicate with other modules. And if you zoom in, again, you end up with all the amygdala region and the VTA and the interpeduncular nuclei in that same module. So nicotine withdrawal is associated with a decreased modularity, and there is a clustering of the amygdala region, the ventral midbrain network, that VTA interpeduncular nuclei network. So can we go down one level and try to modulate those neurons, those neurotransmitter systems? So as Iman mentioned, there is probably a crosstalk between pain and nicotine dependence in the ventral tegmental area with dopaminergic neuron. He mentioned hypodopaminergic function in nicotine dependence and pain. What you see here are animals that are dependent on nicotine. You see that they have a decreased firing of dopaminergic neurons. So this is electrophysiology done in vivo in anesthetized mice. And you see that during withdrawal, you particularly see that decrease in firing. And that was about 9 years ago, 8 years ago. And then at the same time, another group showed that you could decrease the dopaminergic firing. This was to an appetitive stimuli using a CRF injection locally. So there is an idea that CRF peptide might be mediated this hypodopaminergic function. So at that time, we were looking for CRF neurons in the CEA, and we didn't see much modulation by exposure to nicotine. On the other hand, we found that. So on the right side, those are stars that were discovered by Hubble that belong to no other solar system. People always thought that stars always had to be in a solar system, and those were found outside solar system. And those are CRF neurons that are in the ventral tegmental area. And so this is the brain reward system, right? We knew that we had dopaminergic neuron, glutamatergic neuron, GABAergic neuron, but not really CRF neuron. Those are stress neuron. And you can typically see them after exposure to nicotine. At baseline, you don't really see them. Very, very difficult to see them. And so we found those CRF neurons in the ventral tegmental area. In mice and in humans, we show that they are actually colocalized with dopaminergic neurons. So they are dopamine/CRF neurons. So we call that the dark side within the brain reward system. We have some preliminary data showing that the number of those CRF neurons in the VTA may be related to the smoking status. So this is human brain samples of smoker and non-smoker, and you see that the smoker have a higher number of CRF positive neuron, a higher ratio of CRF to TH positive neuron, a higher number of CRF of the density of CRF neurons. It needs to be replicated to have a higher sample, but it's really indicative that those neurons may be critical for tobacco use disorder and nicotine dependence. So can you manipulate those neurons? This is work done in rats where we inject a short hairpin RNA that prevents the production of CRF mRNA. So you see we inject it in the VTA. You can downregulate CRF mRNA. You can see it also with PCR. It's very effective. If you do that and you look at addiction-like behavior for nicotine, you can prevent anxiety-like behavior using different tests. Here you have the elevated, no, this is the open field. You have the defensive burring here. And the last one are the elevated plus maze. This is work done also with Andrew Tapper, collaborated with us on that part. So you prevent the anxiety-like behavior. You can prevent condition place aversion. So the animal didn't, well, the assumption would be that either they didn't feel the withdrawal or it was not enough to produce the motivation to avoid the place where they would experience the withdrawal. It doesn't affect acute preference to nicotine, but only focused on place aversion to withdrawal. And you can also decrease nicotine intake, nicotine self-administration, and it's particularly clear after a period of abstinence. So originally, our idea was that the CRF was coming from the amygdala. We show that it's still an important brain region for the control of nicotine intake and anxiety. But there is another source of CRF within the ventral midbrain in those TH-positive neurons, these dopaminergic neurons. We show that it acts locally on the VTA, but it also projects down to the interpeduncular nuclei, which is right below, and to modulate glutamatergic neurotransmission coming partly from the habenula. And so you have two brain stress systems here that contribute to the dark side of nicotine. So let's go, so we've shown that the VTA CRF neuron and the CeA CRF neuron are critical for anxiety-like behavior, hyperalgesia, aversion, and escalation of intake. So how does it work at the synaptic level? So if you patch dopaminergic neurons in the VTA, this is what you have here. This is work done in mice. And then you apply nicotine. It's well known that nicotine will increase GABA release. Okay? GABA release doesn't necessarily mean that the postsynaptic neuron will be inhibited. So here, the work by Jean-Pierre Changer clearly showed that a transient GABA release on those dopaminergic neurons was necessary to produce burst firing, right? So in a sense, it's taking 2 steps back to jump farther. So the neurons is quickly inhibited, and then you have a rebound activation. And so nicotine, the reason why dopaminergic neurons are activated after nicotine is one reason is because you have that short GABAergic transient that you see here. Animals that are dependent on nicotine, they do not show that effect, right? They become tolerant to this effect, a pretty classic mechanism. What we showed is that this tolerance is developed in part by CRF. If you downregulate CRF mRNA in the VTA, you can restore that sensitivity to nicotine. So in other words, what it shows is that nicotine cannot turn on dopaminergic neurons in dependent rats. Okay? If you are dependent rats, you will become tolerant, and that might contribute to this hypodopaminergic function and possibly the anhedonia associated with chronic exposure to nicotine. If you look in the CEA, it's a different mechanism, although nicotine also increased GABA release in the CEA. You see that here. This is the same measure, spontaneous iPSC using patch clamp. What's interesting is that it predominantly increased GABA release onto non-CRF neuron. But when the animal becomes dependent, you have an increased GABA release onto CRF positive neuron. And so the idea here would be that in dependent animal, nicotine turned off the CRF system. Right? So it's very possible that in the CEA might be one of the important locus for self-medication because you can turn off the brain stress system. So I've showed that tolerance, anhedonia, and self-medication may be mediated by the dysregulation of the GABAergic neurons onto dopaminergic neurons and onto CRF neurons in the VTA and in the CEA. Now let's talk about nicotine. Can we prevent the dark side by directly targeting nicotine? So this is a tobacco field in China, and people have described this bacteria, Pseudomonas putida, that lives on those tobacco leaves and use nicotine as its sole source of nitrogen and carbon. So it feeds on nicotine. It produces this enzyme, NiK2, extremely powerful in degrading nicotine. And so we partnered with a chemist at Scripps, Kim Janda, who modified this enzyme to increase its half-life and administered this enzyme to animals that were dependent on nicotine. I'm not showing the work here, but if the animals are already dependent on nicotine using mini pumps, and you give exposure to this enzyme, you can reverse the symptoms of withdrawal, and you can also prevent the development of them if you give the enzyme before. Right? You remove the nicotine, it's going to work, right? Now, the issue is if you do that in an animal model where they actually self-administer, would they compensate for the lack of nicotine? So we show here blood nicotine level after the enzyme. You have a decrease by about 99%. You leave about 2 to 3% of nicotine in the brain, and I think it's important. I'm going to tell you why later. If you give access to nicotine using self-administration in this paradigm, the animal will keep pressing for nicotine. Right? We were a little bit disappointed at first. There is absolutely no nicotine in their blood, but they'll keep pressing. Now, if you give them a concurrent food shock when they take the nicotine, then all of a sudden they stop. Right? It's not worth it anymore. And that reminds me a lot about denicotinized cigarettes, or very low nicotine cigarettes. I've tried those. They kind of work. If you're coming out of an airplane after a 16-hour flying, it's great. Right? You're going to experience a lot of relief from withdrawal. But are they that good that you would buy them again? No. Right? Because they're not that great. Right? So this is what the rat tells you here. I'm going to take that nicotine, that 5% nicotine if I can, but I'm not going to work and get zapped for it. Okay? And then if you test them in animal models of relapse using reinstatement procedure with stress or with administration of nicotine, you see that the animals who were exposed to this enzyme for 2 weeks, they show a lot less relapse, if any relapse, to nicotine self-administration. We also show that those animals do not fall into a precipitated withdrawal. You could block the nicotinic receptor by giving mecamylamine. We thought originally that by giving this enzyme we will produce a precipitated withdrawal, but we do not. And my interpretation is because we leave this 2 to 5% of nicotine that reach the brain, so it's just enough to avoid precipitating withdrawal. So I've showed you that the negative emotional states during withdrawal are a key driving force for the maintenance of use and relapse in animal model, that nicotine withdrawal is associated with decreased brain modularity and activation of an extended amygdala ventral midbrain network, that activation of CRF neurons in the VTA and in the CEA, and dysregulation of GABA transmission mediates partly the dark side of nicotine, and that enzymatic approach may prevent and reverse this dark side. So one more thing, since I have a couple of minutes left. I'm not going to show you the whole study, but obviously in this crowd, I don't have to explain what vaping is. And like Jed said, the hysteria that is developing about it. Let's remind everybody that 500,000 people die every year from tobacco use disorder. So we have, sure, 40 people, 50 people who had death related to that, but it is on a completely different scale yet. So we're interested in looking at nicotine vapor now for a long time. My first paper actually was in 2008, I said 2006, where we showed that exposure to nicotine vapor produce nicotine dependence. We sent a couple of grants, got unfunded. The reviewer basically said that electronic cigarettes were not a thing. I remember going to SRNT that year where the keynote speaker said that nicotine was not addictive and that it would never be a thing. Got another paper showing that animals would escalate their nicotine self-administration after exposure to nicotine vapor. We submitted the grant and got trashed again. Okay, tried again and got trashed again. So you have to be resilient in research and keep going. And we finally got some money. Many years later, we had the program officer actually calling me and say, hey, can you please resubmit your grants? Because we're getting a push from the administration to fund this work. And so we spent many years trying to develop this model of electronic cigarette self-administration in rats. It's not easy, okay? Despite what some people think, it is very difficult. So you have an example here. So this is the setup that we are using. You have multiple animals. Those are custom-made chambers. They press a lever and they get this puff of nicotine with polyethylene glycol and vegetable glycerin. And you'll see that very quickly the animal learn this task and they press the lever and go back to that hole where they get that puff. It's not nose only, it's the whole body exposure, but you really see every animal, every time they go there, they get that puff. And they have this weird behavior where it looks aversive and appetitive at the same time. So sometimes they'll try to put some bedding on it, but they'll go back to it. Right? So very similar in a way to human behavior. You don't like the smell of it, but you still do it. Okay, so I'm not going to have time to go through this data, but we show that rat will self-administer nicotine vapor to the same level than IV self-administration. They reach blood nicotine level about 50 nanograms per ml, very similar to tobacco user. It will produce dependence, hyperalgesia, somatic signs, anxiety-like behavior. They show spontaneous relapse after abstinence, 3 weeks of abstinence. Varenicline administration decreases this behavior. And most surprisingly, it does produce cardiopulmonary abnormalities. This is early study, but we show that there is an alveolar simplification in animals that are vaping nicotine, not the vehicle, just nicotine with the vehicle, and that it remains even after 3 weeks of abstinence. Well, you have to be resilient because this is the review from the paper when we got it back last week. It is meaningless. It is not novel. It's simplistic, just not new. Who cares? Okay? So we're pretty excited about it. Okay? All right, that's all. I want to thank my team, Giordano De Guglielmo, Marcela Calupi, who are now assistant professor at UCSD, Adam Kimbrough for the whole brain imaging, Lauren Smith, the graduate student who did that work, NIH, TRDRP, and the CMCR for the funding and for your attention. Thank you.
Well, thank you, Olivier, for a great talk and a wonderful degree of resilience. And so we do have a couple of questions here. I'll start with Jed, and we'll go to Ahmad.
Hi, really interesting, and that kind of complementary effect of CRF in VTA and amygdala, that kind of counterpoint is really fascinating. Question, have you done any work to see if the CRF response to withdrawal is sort of this indirect, very indirect effect of nicotine withdrawal, or could those CRF-containing neurons have nicotinic receptors on those very neurons or presynaptic innervation of them?
That's what I'm asking my postdoc to look at. So we don't know yet where those nicotinic receptors are. Right? So we have a transgenic rats that expresses GFP in those CRF neurons. So in theory, we could look at that. The problem is with doing immunohistochemistry with nicotinic receptor. It's really, really hard. It's not specific. It's a mess. Right? So we will have to do, I think, single cell analysis using FACS, for example. It's a little complicated. It requires some money, funding, but I would love to look at that. And the subunits, which one do you need to activate? Would be great.
So thanks, Olivier. Fascinating, and especially that's change in brain modules. I was wondering if you need to do the spinal cord and maybe the peripheral, at the dorsal root ganglia. If you're serious about pain and nicotine, right?
Well, I agree with you. That'd be great. Now, the problem is finding someone who's willing to do the dissection and keep everything from the cerebellum, the pons, and the spinal cord. When you ask postdoc, even asking them to keep the cerebellum is like, oh, really? You want the cerebellum? So the other problem is, so it's an automated pipeline for the data, right? So we use the Allen Brain Atlas to match every virtual section onto the atlas. I'm not sure if they have that whole atlas from the prefrontal cortex down to the spinal cord. So we would have to do a lot of work to try to, do multiple type of analysis. The other issue is the size of the sample. Right now, we're really limited in the size that we can use. We have to use mice, not rats, and the brain has to be cut. We don't even have the whole pons, right? Because otherwise it doesn't fit. So it wouldn't fit with the spinal cord. We would have to do, it's just more work. It would be great. I would love to look at it.
Okay, well, thank you. And we'll have further discussion after the late morning session. And thank you, Olivier. So now we'll have a short 15-minute break, and we'll reconvene for the second morning session. Okay, thanks.